This video lecture covers chapter 16, which begins our unit on weather and climate. So we'll start with the atmosphere. The atmosphere of Earth is very unique. It's what allows life to exist on Earth and the reason why we don't have life on other planets. Other planets have atmospheres, but none of them have the composition of the atmosphere like our Earth. So when we look at the focus on the atmosphere, we're going to focus really on looking at weather and climate and why and how the atmosphere can influence those. So what is weather? Well, weather is constantly changing. This is the day to day or even hour to hour pattern that exists from the atmosphere. Whether we have clouds or sun or precipitation, that's weather. And why is weather important? Well, it impacts our lives. Okay, I know in my house, every morning we get up, we ask Alexa what the weather's going to be like. We want to know how to dress. Do we need to wear a jacket? Do we need to wear shorts or jeans? Should we carry an umbrella? Okay, so the weather definitely impacts our daily lives. Effect on the economy, effects on agriculture, energy use, transportation, energy. And so the weather has a great influence on us, but we also will influence weather, as you'll understand and see more of as we go through these next few chapters. Climate is a description of aggregate weather data. So this is a composite of weather, what has taken place in a specific area over a specific period of time. Climate data can't predict the weather. It can give us a generalization, but it can't predict what's going to happen on any given day. Now, weather and climate can be expressed in graphs. Now, this particular graph shows some climate data for a particular city, showing the record lows, average highs, and record highs throughout the year. And this is based on averages over time and records over time. Okay, we can display weather data the same way. So what are the elements of weather and climate? What are we looking at? Well, temperature, okay, so how much heat there is, and we'll discuss that in this chapter. Humidity, which we'll talk a little bit about, but get back to later on. Cloudiness, precipitation, air pressure, and then wind speed and direction. So these are the 6 elements or the 6 factors of weather and climate that we're going to study as we go throughout these next few chapters. So let's take a look at the atmosphere. So when we talk about the atmosphere and we talk about air, of course, air is a mixture of gases. And this figure here shows you this composition. So nitrogen and oxygen compose the majority of air. Those two together make up, over 99% of air. And we're talking here clean, dry air. So in this graph, what you're seeing here are no particulates, no variable components. We'll get to those in a little bit. So we see nitrogen and oxygen, and then we have carbon dioxide, argon, and then all the others you see there in very tiny parts per million. So we're going to hang out here with carbon dioxide for a minute. This figure here is in your book on page 489, and we're going to watch a little smart figure video here in a second. But why is carbon dioxide important? If we flip back to this pie chart, we see that carbon dioxide only makes up about 405 parts per million. of air, but it's very important. It absorbs energy that's emitted by the Earth and influences the heating of the atmosphere. It enhances the greenhouse effect, which we'll get to a little bit later in the chapter. So we want to know what is happening with the levels of carbon dioxide. The proportion in the atmosphere is relatively uniform, but its percentage has been rising steadily for the past 200 years, really since the Industrial Revolution. So now let's take a look at this smart figure that is going to discuss what is happening with these carbon dioxide concentrations.
Hi there, this is Callan Bentley. Welcome back for another smart figure. After watching this video, you should be able to describe the trend of the Mauna Loa CO2 record and relate it to atmospheric processes, including climate change. Scientists have been measuring carbon dioxide levels in Earth's atmosphere for about half a century. A sampling program was set up at Mauna Loa in the late 1950s by Dave Keeling. As a result, this is called the Keeling Curve. Basically, what you see here in red are the monthly CO2 levels. The overall trend basically has been smoothed out to take away the seasonal signal, and that's the black line there. So essentially what you see is that every time the graph goes up and then down and then up and then down and up and down, what you're looking at there are seasons. Basically in the northern hemisphere summer, a lot of carbon dioxide is drawn out of the air by plants, and so you get lower levels. In the northern hemisphere winter, most of the plants are not undergoing photosynthesis, so carbon dioxide levels creep up again. And in spite of that seasonal signal, you see that there's this overall trend towards higher and higher levels over time. That increase is of some concern because it represents a perturbation to the climate system. The ice cores that have been collected at Vostok in Antarctica have shown that CO2 levels have varied over the past million years or so from about 180 to around 280 parts per million. And then, starting with the Industrial Revolution, we've completely left that envelope of normalcy, and CO2 levels are at around 395 parts per million right now, and they're climbing fast. If you consider what the Earth's climate is doing, and you only consider natural forces, that basically gives you this blue line that goes across the bottom here. So naturally, we would expect the climate to be more or less stable. However, if you also consider the anthropogenic effects, in other words, the human production of CO2 and other perturbations to the climate system, you would expect to see something in this pink band. And what we actually observe is shown in black. You can see it's right there in the middle of what we would expect if we consider both natural and human forces that are influencing the climate system. Let's wrap up our discussion by traveling down to the South Pole. This is the Amundsen Scott South Pole Station, an American scientific research facility that's located near the South Pole. One of the things that they do here is that they record the level of CO2 in the atmosphere. So what would you predict for the CO2 concentrations at the South Pole as compared to, say, Mauna Loa or some other northern hemisphere location? Take a minute to think about that, and then we'll take a look at a graph. All right, so here's the promised graph. Here's the data from the South Pole. The South Pole line is the line that's shown in black. The blue line is actually from Alaska, from the northernmost part of Alaska, Point Barrow, way up on the Arctic Ocean. So one of the things that you'll notice here is that when Barrow's numbers go up, the South Pole's numbers go down. So basically that's, again, the seasonal signal that we talked about at Mauna Loa. When it's the northern hemisphere's winter and carbon dioxide levels are at their maximum, it's the southern hemisphere's summer. And so the plants there are drawing down CO2 levels. But there aren't a whole lot of plants in the southern hemisphere. And in particular, there are no plants in Antarctica. And so as a result, you see that the overall amount of variation in the South Pole's line is much less than at Barrow. So Barrow has a really big seasonal swing, up and down, up and down, up and down, but the South Pole has a relatively limited seasonal swing. And then, of course, the other thing that you notice here is just like at Mauna Loa in Hawaii, both Barrow, Alaska, and the South Pole show increasing carbon dioxide levels over time.
So as you saw there, the levels of carbon dioxide are very important for us to monitor, especially looking at, seasonal and longitudinal and latitudinal locations. So the next section that we're going to talk about are those variable components. So in addition to those major components we saw on the pie chart, we also have different gases and particles whose quantity varies based on location and different times of the day and times of the year. So we're going to look at a few of these: water vapor, dust particles, and ozone. So I'm going to discuss water vapor here, and then I'm going to show two smart figure videos, one on aerosols, and then another on ozone. So water vapor is basically the humidity, okay, which is just the level of water vapor in the air. And we'll get to more about that in the next chapter. The amount of water vapor in the air is going to vary considerably, from practically none up to about 4% of volume of the air. Why is that significant? Well, because it's the water vapor, it's the humidity that are responsible for forming clouds and precipitation. It also has other roles, one of those being that it absorbs heat energy from Earth, just like carbon dioxide does. So it's important when we look at the heating of the atmosphere, which we'll get to here in just a minute. So now we'll watch those two smart figure videos.
Well, an aerosol, the physical definition of it, it's a small particle which is suspended in the air, can be suspended at any altitude, but our main interest is in tropospheric aerosols, which are suspended at altitudes essentially from the ground to about 8 kilometers in the atmosphere. The total number of aerosols in the atmosphere is extremely large. It's like the number of stars in a galaxy. And those are tiny particles. Most of them are invisible to a naked eye, but there are very many of them. Aerosol particles can be natural and can be created as a result of human activities. And so those particles are called man-made or anthropogenic. Natural aerosols can come from all places. For example, desert dust is blown off the surface of the Sahara Desert, the Asian deserts, the Australian deserts. Sea salt particles are produced when ocean waves break. They produce a lot of tiny salt particles. Essentially all kinds of fires produce aerosols. Volcanoes, they throw out a lot of volcanic ash, and those are also natural aerosols. And all kinds of human activities produce different kinds of aerosols, and the most typical example would be sulfate particles, the result of combustion, or soot particles. On average, an aerosol particle is estimated to live for about a week. Aerosols are produced, they're transported, and eventually they disappear because they are rained out, for example. Aerosol particles can differ by their size and by their chemical composition and by their shape. And all these inequalities can be mixed together, and that's what makes aerosols so difficult to study. At any given location, particles of different types and of different origins can coexist. If a particle is, for example, generated somewhere in China, it can be transported to the United States of America. So this transport from different places makes the aerosol population at any given location extremely complex. They have several roles in affecting climate. For one, they simply reflect sunlight back to space, and this effect amounts to cooling of the atmosphere and the surface. But the same particles can also absorb light, and by absorbing light they become warmer and they warm the surrounding air, so this effect is to warm the atmosphere. And how much light is reflected and how much is absorbed depends on the chemical composition of the particles, on their size, even on their shape. There's another effect that aerosols exert on climate because they affect the properties of clouds. And clouds are a major modulator of the amount of energy that reaches the surface and warms it. And so by changing the properties of clouds and precipitation, the aerosols can also affect climate. The most important knowledge that we have is that aerosol particles are extremely complex. So we need to study the distribution of particles globally, and the only way to do that is from satellites. The knowledge about aerosols that we have tells us that the instrumentation on this satellite must also be very complicated, and with this instrumentation we must be able to infer many properties of the aerosol particles from space. And that's the purpose of the aerosol polarimetry sensor, which will fly as part of the GLORY mission. We are not interested so much in the total number as how they are distributed, because their distribution affects local climate, and that's why we need to know this distribution with very high accuracy.
Hi there, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe where the ozone layer is, how the hole in it formed, and what the implications are for human health. So if we look at a vertical slice through the atmosphere, we'll see that the atmosphere changes with increasing distance above the Earth. You and I spend most of our lives down in the troposphere, but the layer above the troposphere is called the stratosphere. And about halfway up through the stratosphere, somewhere between about 20 and 30 kilometers above ground, which is on the order of around, call it 15 or 17 miles above the ground, that's where we see a concentration of this molecule called ozone. Ozone is oxygen, but unlike the normal oxygen that's O2 that we breathe every day, ozone is O3. It's actually a health hazard to breathe it, so you wouldn't want to breathe it, but you should be glad that it's up there. The ozone layer protects us from incoming ultraviolet light from the sun. So the ultraviolet light, some of it bounces off that ozone layer and doesn't make it down to the Earth. Some of it still does make it down to the Earth, of course, which is why you can get a suntan if you spend time outside. But the ozone layer filters out some of the incoming ultraviolet light. Now the ozone hole is a thinning of the ozone layer that is most concentrated over the South Pole, but also exists over the North Pole. There was a lot more ozone back in the day, and then it started thinning out around the late 1970s, early 1980s. And you can see that the ozone hole got bigger and bigger and bigger, and then it kind of leveled out around the year 1995 or so. And it's hope that in the future it's going to recover and the ozone hole will get smaller over time and we'll have a thicker ozone layer over the southern part of the southern hemisphere. The reason that the ozone hole stopped getting bigger and stayed about the same size is in the mid-1980s there was a realization that human activity was causing the hole in the ozone layer, that we were releasing chemicals called chlorofluorocarbons, or CFCs, into the atmosphere. And these were used as propellants in spray cans, they were used as refrigerants. So basically when these things were released into the atmosphere, they did two things. One is that they had a reaction with the ozone molecules where they basically ripped them apart. But also these CFCs were really, really stable, so they stuck around in the atmosphere for a very long time. So each CFC molecule could rip apart many, many, many ozone molecules. The ozone hole over Antarctica was a certain size in 1979, but it got to be much bigger than that. This is what it looked like in the year 2012. You can see that there's much, much less ozone over Antarctica. Why does this matter? Well, people in these places are at higher risk of skin cancer, of developing cataracts, and all that extra UV light actually harms the immune system as well. So there's a bunch of negative health effects from it. We should be grateful that this problem isn't worse than it is. If the Montreal Protocol banning the use of chlorofluorocarbons hadn't been enacted, then probably there'd be a lot less ozone up there and a lot more skin cancer around the world. So if you were to go up to, say, 30 miles above sea level, which is somewhere on the order of around 47 kilometers above sea level, what would be the two things that you'd have to worry about most? Well, as you have no doubt guessed, you are going to be above the ozone layer at that point, so you wouldn't have the protection of the ozone layer, so you'd need to wear some sort of protective clothing to shield you from the ultraviolet light from the sun. You wouldn't have to worry too much about the temperature, because the temperature actually, after decreasing throughout the troposphere, rises again through the stratosphere and basically reaches a maximum there at the top of the stratosphere. But You'd have to worry about oxygen because you may be aware there's less oxygen the higher you go in the atmosphere, and even climbers at the top of Mount Everest often use supplemental oxygen, and you'd be many times higher than the top of Mount Everest. Hopefully you thought about those. Maybe there's some other hazards that I didn't cover, like that meteor there, but at any rate, I thank you for your attention.
So there, from those two videos, you were able to see the effects that aerosols and ozone can have on the composition of the atmosphere. In the last video, you got a little bit of an introduction to the vertical structure of the atmosphere with the figure that he was showing you there and going over. So we're going to come back to that a little bit more, but first we'll talk about the air pressure changes, which he also did allude to there. So air pressure changes with altitude. So what is air pressure? Well, that's the pressure of the weight of the air above us. Okay, so as we're walking around here on the surface of the earth, the air around us and above us is pushing down on us. That's referred to as air pressure or atmospheric pressure. At sea level, the average pressure is a little bit more than 1,000 millibars, which is about 14.7 psi, or pounds per square inch. As we go higher, the air pressure is going to decrease, okay? Because there's less air, then that means it's going to have less force as it's, pushing down on us. There's a figure in your book on page 491 that shows Mount Everest and then a balloon. They're going way up into the atmosphere. But looking at, I might have that, there we go. So you can see that the air pressure at the top of Mount Everest is 314 millibars. So we've gone from about 1,000 at sea level to just a little more than 300 at the top of Mount Everest. And then all the way up here in this balloon, where this Captain Kittinger got, it was 9.6 millibars. So less than 1% of what it was at sea level. So 1/2 of the atmosphere lies below an altitude of 5.6 kilometers. And that's what this dotted line is showing you here. At about 16 kilometers or 10 miles, so right at this line here, 90% of the atmosphere has been traversed. And then above 100 kilometers, only 0.00003% of those gases that make up the atmosphere are left. So if we look at what happens with temperature, we'll go to this figure that you saw in the last Smart Figure video, and we will divide the atmosphere into 4 layers based on its thermal structure or its temperature structure. So the lowermost level you see there is the Trophosphere. That's where, where we live. Temperature decreases with altitude. Trophosphere means where air turns over, and this is how air is able to vertically mix. This is where our weather phenomenon occur. That's why you see those clouds there. The thickness of the troposphere is not the same everywhere. It varies with latitude. It varies with the season. The outer boundary there is called the tropopause. So that's the boundary between the troposphere and the stratosphere. The stratosphere, the temperature remains fairly constant until it gets to a height of about 20 kilometers, and then it's going to start to increase up to the stratopause, which is about 50 kilometers. Temperature is going to increase there because this is where we have that ozone layer. The ozone layer is going to absorb the ultraviolet radiation, so it's basically heating up that air. So the stratosphere then is going to increase in temperature. Above the stratosphere, we have the mesosphere. Temperatures again are going to decrease with height until we get up to the mesopause, which is about 80 kilometers or so above the surface. The coldest temperatures anywhere in the atmosphere are going to occur at the mesopause. So you can see this temperature here much lower than any of the other temperatures that we've seen. Accessibility is very difficult at this area. It's one of the least explored areas. Then we get to the thermosphere. This is the fourth layer, really doesn't have a well-defined upper limit. It contains only a fraction of the Earth's atmospheric mass. You'll also see as we go throughout the thermosphere, the temperatures are going to start to increase because we get absorption of the high energy solar radiation here by the little bit of oxygen and nitrogen that are left. So that is a quick look at the temperature changes within the atmosphere. So our next section kind of explores the relationships that we have between the Earth and the Sun. And this is what explains the seasons, what causes the seasons. This is also what leads us to how the days get longer in the spring and then shorter in the fall. So if we look at the Earth-Sun relationships and why they're important, well, nearly all of the energy that drives weather patterns on Earth is from the Sun. Earth intercepts only a minute percentage of the energy given off by the Sun, less than 1/2 of a percent. But that energy is not distributed evenly over the surface of the Earth. The amount of energy that's received is going to vary by latitude, by the time of day, and by the season of the year. And this unequal heating is what drives the ocean currents that we looked at in the last chapter, as well as what creates winds. So there are two motions that we have when it comes to the Earth and the Sun. I think I have, no, I don't have a figure this. So yes, I do. Hold on, let me get a little bit ahead. All right, so if we look here at the Earth, we'll see this axis, okay, and the Earth is going to rotate on its axis, okay, so this is its rotation every 24 hours. That's what gives us our daily cycle of daylight and darkness. And this line that we see here, okay, is called the circle of illumination. Sorry, my mouse is being a little spastic. So this line here that separates the light half from the dark half is called the circle of illumination. So this is due to the Earth's rotation every 24 hours, okay? Then the Earth also exhibits another motion called revolution. And that's how it revolves around the Sun. It makes one slightly elliptical orbit around the Sun. And so sometimes this is referred to as its orbital motion. So rotation is daily. The revolution is yearly. The orbit of the Earth is not perfectly circular. It's a little bit more ovoid in shape. So the distance is going to vary at different points of the year. January 3rd is when we're closest to the Sun than at any other time. This is called the perihelion. And then on July 4th, we are the furthest away, and that is called the aphelion. And so you think, okay, well, that's what makes up the difference in temperature, but it's not really. That's really only a minor role. It's going to be more of the changing sun angle as it rotates and revolves around the Sun and the changing length of daylight. So if we look at this figure here, this kind of gives us a picture of the changing sun angle. So it's when we look at the angle of the sun, that gives us our length of daylight. It also gives us the amount of illumination or the area that is illuminated at any given time. So now we're going to watch two more smart figure videos looking at the angle of the sun's rays on Earth, as well as Earth's orientation as it moves around the sun.
At the equator, incoming sunlight hits the ground straight on. So 1 unit of sunlight is spread over 1 unit of ground area. It hits at a 90-degree angle. But at other latitudes, the story is different. At mid-latitudes, that same 1 unit of sun is spread out over a larger area, 1.4 units, say, when it hits the ground at a 45-degree angle. In the far north, that same unit of sun might be spread out over 2 units of ground if it hits at, say, a 30-degree angle. Let's use an analogy, a flashlight. The flashlight's putting out a constant amount of light, but if you change the angle between a desk and the flashlight, you'll see that that light is spread out over a larger area. Hi, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to define a solstice and distinguish it from an equinox, and describe how both days relate to the orbit of Earth around the sun. One of the most fundamental facts that you need to know about how our planet works is that our planet orbits the sun in a plane. That plane is sometimes called the ecliptic, or sometimes it's referred to as the plane of the solar system. But the axis around which our planet spins, the axis of rotation, is not oriented 90 degrees to the ecliptic. So here in this picture, that line's like 90 degrees to the ecliptic, but you can see that our axis is at an angle relative to that. That angle is around 23.5 degrees. This axial tilt is the reason for the seasons. In the northern hemisphere summer, you have the northern hemisphere tilted more towards the sun. So that's what's shown over here in the upper left image. The polar regions here are getting 24 hours of sunlight per day because they're always in the sun. And at the equator, there's around 12 hours of sunlight per day, while down in the southern hemisphere, there's less, like 9 hours in Buenos Aires, Argentina, for instance. Now, if you go and you think about the opposite situation, the winter solstice in the northern hemisphere, you see the exact opposite situation. Down there in Antarctica, they're getting 24-hour sunlight. In those circumstances, the equator is still getting about 12 hours of sunlight. And up in the northern hemisphere, in North America, for instance, where probably most of us live, they're getting about 9 hours of sunlight, and then the rest of the day is dark. The midpoint between these two extremes is considered the equinox. The word equinox means equal night, and that means that the day is equal in length to the night. During the equinox, the sun's rays come in from the side, parallel to the lines of latitude, and you can see that all over the face of the Earth there, we're getting 12 hours of sunlight for that one day of the year. So this relates to the orbit of the Earth around the sun because that axis is always oriented in the same direction. So that's over towards the North Star, that'd be up over here somewhere, and you can see that that north polar axis is pointing in that direction. When the northern hemisphere is pointed away from the sun, that's the winter solstice. When the northern hemisphere is pointed towards the sun, that's the summer solstice. So longest day of the year over here on the left, shortest day of the year on the right. And then in between are the equinoxes. So here's one equinox and here's the other. There's one equinox in spring and one equinox in fall. And those are the days, of course, when the day is equal to the night. So let's go back to this image we started with here. Which day of the year is depicted in this image? Hopefully you notice that the proportion of sunlight in the southern hemisphere is much, much greater than the proportion of sunlight in the northern hemisphere. So that must mean that it's the southern hemisphere's summer solstice, and that's the northern hemisphere's winter solstice. Good job. Hope you figured that out.
To avoid making this particular video too long, I'm going to stop here and we'll say that this is going to be part 1, and then we'll pick back up with section 16.5 in part 2.